Recording is on.
Okay, hi everyone. So last week we discussed about this one, right? The building the max heap using the array and also finding the kth smallest element in the array, right? So we will iterate this problem again. This is complicated and very important problem. That's why we are going to discuss this again. And so first, let's understand why we doing this. Let's compare. We already solved the finding kth smallest element using min heap, right? So now we are solving we using max heap. So let's compare those algorithms. What is the advantage and advantage of using max heap than min heap, right? So Karina, would you explain again, just so that since we are recording, so and Arvind also here, so that then I will show the code. Would that be okay?
Yeah, sure.
Yeah, so let's do one thing. I will stop sharing. I think even if I stop sharing, it will record. I think you start sharing and explain again, so that then I will show the code. Okay, I'm stop sharing it. Okay, you share it. Yep, you can. Yeah, you can use the same example. I hope it will record the whole your screen also. Let's see. Yeah, currently I think you muted. Can you unmute? Yeah,
Sorry.
now we can. Yeah,
Yeah. Here is the array. The problem is we are going to construct a heap using an array. And now, previously we have seen a min heap. Now we are going to construct a max heap and find the k smallest element in the given array. So consider an array of 9, 7, 1, 3, 5, and 4.
yeah.
So in this array, let us consider k is equal to 3.
Yeah,
So
and
we
what is
have to
the
find.
so, so before even going to the heap, just to give a concept of from the interview perspective, they don't ask you, they don't even tell you about the heap, right? So
Yeah.
they will simply say, "Hey, we need to find k smallest." Okay, so then if you come up with a normal approach, let's say what are the different data structures available? You can use just normal loops, and you can use hash tables or queues or stacks. And why they are not working? So can you give that reasoning? Because you can use hash tables, let's say, or you can use trees,
Yeah.
stacks or queues. So what is the advantage of, what is the reason behind creating this new data structure?
We
Okay.
can use hash tables, but we have to store a key value along with the value we are storing. There
Yes.
is a space complexity. For example, I have some 10 elements here. What if I go for billion and 100 billion elements? So it will
Yeah.
complexity, space complexity will also increase along with the elements I'm
Yeah.
going to insert into the table.
And
And
also, since it is, let's say, kth maximum, sorry to distract, so let's say kth maximum or kth minimum, these are looks like if the elements are sorted, it will be easy to pick, right? Because array is not sorted, right?
yeah,
So the first basic, the very the first solution that comes into our mind is, hey, let's sort the array, right? If you sort the array, you can just find based on the index, you can find third maximum, fourth maximum, fifth maximum, whatever you want, you will get it, right? Not only just kth maximum, you can find any kind of maximum, right?
yeah,
That is sorting of the arrays is kind of very, the first answer. When somebody asked about this question, hey, we can sort it, and I will give you the kth maximum. So then, what is the problem there? Why can't we do that? Rather, why we need to build a min heap or max heap? Can you answer that?
the
why
sorting
why don't we?
algorithm will also take uh,
Mm.
itself from O of n square to O of n log to n time complexity.
Yeah, n
So
log
it
n
is
is
one of the problem.
yeah, yeah.
After sorting, we have to find the element in the array. Maybe if it is the least element, the first element will be returned. If it's the maximum element, the last element will be returned. What if the element in the middle of the first and the last? So we have to go through the array again.
No, I think if you sorted, you can simply get, let's say, kth element. It's k equal to 3, right? If it is
Yeah,
sorted, it's a of 2, right? A of 2 is the third maximum. Let's say you sorted in increasing order. Okay,
yeah,
so if kth minimum is k equal to 3, the kth minimum is a of 2, right? You can get with order of 1 complexity, right?
yeah,
So, so if you sorted, you can get the value, the final result without any problem, without any loops or anything. So you can just kth minimum k equal to 3, a of 2. Let's say k equal to 10, a of 9, right? Because the
yeah,
index starts from 0, right?
yeah,
So as you said, one thing is the main problem there is sorting. First, you need to sort the entire array, which is not, which is a huge operation, right? And the other
yeah,
thing is, you need to say like the input can, let's say, the input is not a constant array. Let's say you have only 6 elements here, right?
yeah,
So if the input is keep on coming, let's say it's kind of stock market or something, every day you get a value, stock
mm,
price. Okay. If you are keep getting the values, you need to sort every day. You need to sort the entire array every day in order to get this value correctly,
yeah,
right? But if you have this min heap or max heaps, you can just simply look at the latest value which is added to the array, correct?
yeah, yeah.
So you
And
you
it
no
is a
need to
lot
worry.
faster than sorting an array.
Exactly. So next day, let's say you got another value added at the end of the array. So you can simply check that value whether that will go to the heap or not. So you are maintaining a smaller size of heap, and you also you also not sorting the array, right? And as the values are coming, you can simply compare with the top of the heap, and then you find the values. That is advantages here. So why we going with heap is, these are the two reasons. Did you
Okay.
understand that?
Yeah, yeah, yeah.
Yeah, Arvind, is it clear? So why we are creating the heap data structure rather than sorting the array?
Yeah, yeah, Suresh. Clear.
Yeah, that is the main difference here. Yeah.
Mm.
Go ahead now. Yeah, now you explain. So this is basically like from the interview perspective. If they ask about this question, you need to explain that, hey, we can sort the array, and but these are the drawbacks. That's why I'm not sorting the entire array. I'm going with a heap data structure. Then they will ask you about what is the heap and how it works, what is min heap, what is max heap. If they ask you, if they don't ask about it, you can just simply explain, hey, I will create max heap, and max heap means the maximum element on the top. So you just go ahead explaining the rest of the algorithm how it works. Yeah. Okay. Now go ahead and explain
Yeah.
the max. Yeah,
Uh, we already know heap is a complete binary tree, so it can be easily stored in an array.
exactly. Yeah,
So here the problem is we have to find the third minimum element in the array, which is 4
yeah,
exactly. Yeah, we have to come up with this answer 4. So for that, previously in min heap we used to create min heap for the n elements in the array, all the elements which is there in your array. But for here, since we have to find only the third element, we are going with 3 elements, 0, 1, and 2, and randomly taking the first 3 elements
yeah,
and constructing a max heap. So by max heaps 971 there as it is, because
Yeah.
9 is the biggest element in the array and it is the root.
Yep.
So uh, now we have an understanding that all the element in the array is less than 9.
Yep.
So if we find any other element which is less than 9 in the rest of the array, we have to include it into this array, into the heap, sorry, into the
Heap.
heap and
Yep.
shuffle it, so that we'll come up with the minimum, third minimum value. So for that, we are comparing this root with the next element, which is 3.
Yes.
So the concept of max heap is that construct the k element heap and compare the rest of the array with the root of the heap, so that uh, we'll construct the heapify, max heapify, and come up with the minimum element at the last. So now 9 and 3 compared, 3, possibly 3 will fall under 9. So we are replacing 3 with 9. So 3, 7 and 1. So we are going to heapify this heap, max heap. So this will be becoming 7, 3 and 1. So now 7 is the root. So we compare the 7 with the next element, which is 5.
Yep.
5 is less than 7. Again, we are going to replace the root, which is 5,
Five, three,
3,
one.
1. Now, it's if you construct a max heap, it will be in order. So the
Yeah.
5 is
You
the
no
root.
need to do basically you will try to do the top down heapify, but nothing will change, right?
Yeah, nothing will change.
Yeah.
Then, and the last element in our array is 4. We are going to compare the 5 and 4. So which is
You will get the four.
5 will be replaced by 4,
Yes.
3 and 1, and root. Again, the heapify won't change any order. So
Yep.
now the answer is the maximum, third maximum element is 4. Here,
Yes.
instead of constructing uh, the heap for the whole elements, whole array of elements, we are constructing only for 3 elements and shuffling it down. And for each shuffling, we are going to come up with the log k operations. Uh, the space is reduced dramatically by comparing the min heap operation. Min heap. Yeah.
Yeah. That's
Suresh.
good. That's good. That's good. Yeah. This is what the actual algorithm, right? So the main advantage here is less number of space. We are not building a heap with all the elements, right? So
One question here, just when we are sorting the element of the less size, let's say three elements, so that will take log of k, or should it be k log k? Like,
sorting you mean like creating the heap?
no, no, uh, like we are
Not
taking one
sorting.
element from the array and then comparing it with the maximum max heap, the
Yeah.
value present, and then if that element is lower, then we are inserting that element and replacing the max value, and then again we are sorting that, right? So
It's
that
not sorting. It's not sorting. You need to say like heapify,
heapify,
because
okay, okay,
yeah,
heapify,
because
yeah,
we
yeah,
don't change all the
mm-hmm.
values in the array, right?
Yeah,
So
yeah,
it
yeah.
will do the top down heapify. The top down
Mm-hmm.
heapify is log k, because k number of elements, right?
Mm-hmm. Okay, okay, yeah.
So at max, the element which you added on the root, it will go to the bottom. If it is very smallest element,
Mm-hmm.
it definitely go to the bottom, right? Bottom
Yeah,
means the
yeah.
last. It will go to the end of it. So we will replace with the children, and then you'll replace with another children, and then it will go to that children. It will go to the leaf node. So in that situation, log k is the complexity. Yeah.
Okay, okay, yeah.
Yeah, if
Thank
you are
you.
replacing every element, it will be order of n, but order of
Mhm.
k. But we don't replace any elements, and not all the elements, and we don't shuffle. We don't sort
Mhm.
the elements. That is the advantage.
Yeah.
It's not full sorting. It is just heaping.
Heapify. Yes.
Yeah,
Mm.
heap is a little different operation because that will be more beneficial if you want these kind of small values, or the smallest value all the times, or maximum value all the times. So that will be the main advantage of heap. Yeah. So you can draw in a tree kind of structure, Karanya, so that it will be easy. Yeah, let's say 971, right? So
Okay.
9 is on the root. Yeah.
7.
Yes. Now 9 will be replaced with 3,
Yeah.
right? So now what it does is so
3,
yeah.
7, 1.
So now here is, so how 7 will come up, because we need to find a maximum out of these three, right?
Yeah.
So it's like 7 could be on the right, or 7 could be on the left. We don't know. So the right value could be maximum, or left value could be maximum. So what we need to do is basically we'll find the maximum out of all three nodes, right? The parent, left child, right child, correct?
Yeah. Yeah.
So if that maximum need to go to the top,
Mm.
okay? So if
Yeah.
the maximum is the left node, we'll exchange with the left node. If the maximum value was on the right node, we'll exchange with the right node. That is the complexity of that uh, the statements in the algorithm. Yeah, right.
So, yeah. So the heap will be
Yeah.
like
So if
this.
you yeah if you open the top down heap algorithm at this location, I will explain how this 7 will go up and how the 3 will go down. So can you
Okay.
open at the same time? You have the
Yeah.
link, right?
Yeah. Yeah.
Because that is complex part to understand why how we are doing this particular step is the complex part to understand in the algorithm. Open the algorithm.
Yeah. One second.
Yeah, it's in the channel, or if you want I can share the link.
Can you see this algorithm in my? No.
Mm. You already opened it? No, I think you need to
I
look at.
close this open board actually.
Okay, okay. Yeah, you can drag that window into this monitor. Are you using? Okay, you close you stop sharing it.
Now I'll share.
Yeah.
Yeah, Suresh, can you see my
Yeah.
desktop?
Now I can see. Yeah.
Yes. Yes.
Now, if you go to the replace top, that's what we did, right? If you go to the replace top method, scroll down and you can see that in the heap. Yeah, in the max heap, there is a bottom up heap by insert is there, swap is there. If you go down, there is a replace top.
Yeah.
Yeah. See that replace top. This is exactly what we're doing, right? Um, um, yeah, if you go to the replace top, what we do, we will replace the value at a of 0, right?
Oh,
So you canceled 9, and your 9 replaced it with 3, correct? In the board, that's what you did, right? Now what we're doing is top down heapify starting with 0, right?
yeah.
Now go to the top down heapify method.
Top down EP5. Yeah, it is
Yeah,
here.
exactly. See, this is the complex piece to understand. So now this is the parent. That's the integer, that parent represents the index of the parent, right? Now left child is parent into 2 plus 1, and parent into 2 plus 2 is the right child.
Right
You
side.
know this formula, right? So
Yeah.
this is a formula we have to by heart. So this is very important, like how to navigate in the array. If I give you an index, how where is the left child and where is the right child. So it will be like parent into 2 plus 1, that will give you the index of the left child, and parent index into 2 plus 2, that will give you the index of the right child. So since we are not shuffling or the sorting the entire array, we will only compare with parent and its childs, right?
Yeah.
Now we are creating a variable called max. We want to find what is the index of the max, right? See, we have three elements. You have, if you look at the, if you go back to the board, if you go back, can you go back to the board you created? Or is it difficult? Yeah, it is. Yeah, go to that board. Oh, you lost all the things you wrote?
Yeah, actually, this is the problem with this open board.
I see. Oh, if you go back, it will, everything will be erased.
Yeah. Yeah.
I see. Yeah, you can just draw as a diagram. So you have nine at the nine, not nine, three at the top, right?
Three,
371, right? Yeah, three,
7.
7, 1.
One.
So now what is the parent index here? Yeah,
Now, parent index is,
0, because it's just a three elements, right? That is
yeah.
0. We don't need the entire A. So we don't need the entire, no, we don't need that entire array. So we
Okay.
are just focusing on the max heap, right?
Okay.
So the max heap has three elements, 3, 7, 1, right?
Yeah.
So what is the index of 3? Index
Index
of the
of
root
3,
is
3 is 0, the root.
exactly 0. And index of the left node is 1.
1.
And the index of 1 is 2, right? Index of right node, yeah. A
Yeah.
of 0, A of
Yeah.
1, that's good. And this is A
Yeah.
of 2. Now we so since it is on the board, you can see, hey, 7 is bigger. But in the algorithm, in the program, how to find the index of the max. So there are three elements. Okay, parent index is 0 and left node is 1, right node is 2. Now we need to find the index of the maximum element, right? So
Okay.
now if you go back to the algorithm, we are trying to find, we are assuming max equal to parent. At the line
Yeah.
number 123, we are like not assuming, we are putting an initialization. Okay, let's assume that maximum is the parent. But now, okay, no, it's just scroll up again. Yeah, I think it's on the top down heapify. Line number, yeah, line number 124. Now, if you look at line number 124, what are we doing there is left child. Left child is less than current. You know what is current? Did you remember? Current is
Root
the
element.
max number of elements.
The root element we are having now is the current element, right?
No, no, current represents the
Okay, the
next.
array a maximum of element. The
Exactly, a
maximum of
maximum.
elements.
Basically, that will tell you how many number of elements. So
Yeah.
basically, if you have three elements, current will be 3. So that means the index is 0 to 3, 0 to 2. So if the left child is less than current, why we need to do that is, if you are comparing with the leaf node child is, it will be greater than current. So you no need to compare anything. If you are already at the leaf node, let's say parent is leaf node. Okay, so if you are you no need to compare with the childs which are not even in the heap. So that's the condition. But let's look at the actual condition here. If the A of left node greater than A of parent, that means A of left node, what is A of left node in the diagram? It's actually 7, right?
Yeah.
So 7 is greater than the parent. What is the parent value? 3.
3.
That's why if that happens, what does it tell you? That means maximum is
Maximum.
left child. So we are the left child index. We are setting the maximum equal to left child index. So basically, we are finding the maximum between parent and left child. First, that's the first step, because we need to compare with the left child or right child. So I took the left child. Okay, so if the value at the left child is bigger than the value of the parent, then we are resetting the maximum maximum variable. What is the maximum now? Maximum equal to left child, correct?
Yeah.
If now what are we doing in the line number 127 is, now we are comparing if the right child value is greater than the a of max. That means if the right child value in the diagram, what is the right child value? Is it one?
One.
One, right? Yeah,
Yeah.
exactly. So one. So now we already compared 3 and 7. We 3 and 7 means we already compared the parent and the left node. Okay. Now we don't know which one is max based on the values. Sometimes the max is still parent, right? Let's say let's say instead of 7, if you have 2 there, what will happen? The max is still the parent, right?
Mm. Yeah.
You have 3 on the top, and let's assume that you don't have 7, you have a 2 there. If you have 2, then what will happen? This condition will fail. The condition at the 124 is false, right? Because a of left child is 2 greater than 3. No. So maximum is still parent. Okay,
Mm.
that's
Yeah.
why. So in the line number 127, we are comparing with the max. You already figured out what is the max between parent and the left child. Now in the 127, we are comparing that maximum value with the value of the right child. If the right child value is bigger than anything, bigger than the max, right, then we need to make that as the maximum. So max equal to right child. This is very complex. This is the complex piece of the whole algorithm, I would say. Why we doing this? Are you understood or not? Because we need to compare the index of the maximum out of these three indices.
Okay.
Are you still following, or is it little complex there?
It is little complex. Uh,
Arvind, how about you? Is it did you get that algorithm? Because this
Mm,
top-down simplify is definitely complex. Yeah.
yeah, yeah, it's somewhat difficult for me as well.
Hmm. Okay. I can explain if you want. I can explain in
yeah.
it by
Yeah.
using a
Please.
Yeah, yeah.
by
Could
using
you
an
please do
example.
that?
Yeah.
Yeah, because for every line, if you are putting the indexes, then it will make sense.
But Suresh, one thing is this like algorithm very important because like
Yeah, but the thing is, it may not be like, I don't think in the algorithm in the interview they will ask you, hey, implement top-down Heapify, but it's better to know like how the Heapify is working, right? So
mhm,
so we
yeah,
don't know, like if someone asks you, hey, if you completed the actual algorithm in just 20 minutes, let's say, or not even 20, 15 minutes, because the actual algorithm is really simple on the top, right? If you look at the main algorithm, you are just creating a, go to the top of the page, Karanya. If you go to the top of the page, you are just building a
Yeah.
heap, and you are just taking the element, right? See, the algorithm is
mhm,
really,
yeah,
uh, yeah, no, algorithm is this one, find kth minimum using max. Go to that line number 33. Show that algorithm. Yeah, if you scroll a little bit down, yeah. See, this algorithm is very like, it's very few lines, right? Just
yeah,
you are creating, you are inserting k elements, and then you are just taking the maximum, right? So for each element, you are comparing with top, and you are taking the top. So if you wrote this algorithm within 15 minutes or 20 minutes, let's say, then they might ask you, okay, implement the heap, or implement what are the operations on the heap. Then you say, oh, there are two main operations, top down heapify and bottom up heapify. Then they might ask you, okay, implement top down heapify. Then then it becomes like complex, right? So just I know it's not super, there is no guarantee that they will ask you that question, but understanding is really important, how these manipulations are going, right? Yeah. So
Suresh.
yeah, go ahead.
Yeah. Suresh. Yeah. In the top down, if heapify we just saw,
Yeah.
since we have only three elements,
Mm-hmm.
this is fit into the picture. What if we have, uh, let us consider k as 5.
Mm-hmm.
So how this work for 5 elements? How?
Yes, five is five elements. We always start with the parent, right? So
Yeah,
top
we
down
always,
heapify starts with zero, right? So
yeah.
now look at line number 134. We are doing top down heapify with max again. So it will go down. So
Okay.
look at the line number 134 there. We will call the method again.
Okay, yeah. Recursively, we are calling it again.
This is a recursive method. Recursive method.
Okay.
So basically, we will call with the maximum, whatever the maximum you found. And what is if? Look at the if condition there. We are stopping. Look at line number 130.
130.
If we find max which is not current root, then do a swap with max number. So basically this is a very important if condition. If so basically if the max is not changing after all the comparisons, if the max is not changing, if it is equal to parent, that means everything is in order. You don't need to go down basically. Okay.
Okay.
Yeah, I can explain you again if you want. This top down heapify is the only complex one. So if you want, I can explain with an example there. Then it will be helpful.
Yeah, Suresh, once, please.
Yeah, I can do that. Let me share the screen and I can explain,
Okay, I'll
because
start sharing.
yeah, it is just fascinating to understanding how this works, because this there is another algorithm called the heap sort. This is another algorithm is there. So then it will be helpful. Okay. So let me share. Yeah. Okay. Look, can you look at my screen here?
Yeah.
Yeah.
Okay. Okay. So now let's go ahead and try with my favorite. This one. This is the one I use. Or maybe let me try. What is the URL of the board you said? Can you give me? Does it require to create an account? Karanya, that the whiteboard.
Open board, open board.
Open BOARD. Open board. Nice. Let's see. Second. Okay, this is the one. Best interactive whiteboard for schools, and nice. Let's see if it opens. Does it require any account or
I
oh,
don't
get
I
open board for
downloaded
free?
it and installed it in my laptop.
Oh, you installed it. Oh, okay, okay, okay.
Yeah,
It's
like
a
yours.
it's an app kind of thing. Okay,
That's an app.
okay. Let's go with this one for now. So because
Um,
it may take time, right? So let me do side by side, because in order to understand the top down heapify, it is very important to have the code on the other side. Okay. I will open this one. This may be easy here. So here is the algorithm we are trying to understand. This bottom up. No, not bottom up. Here is the thing, right? So top down. Okay. Let me put this aside. Okay, let me close this. Okay, now can you guys see the algorithm here on the right side?
Yes.
yes, yes.
Yeah. Okay, I don't know how to reduce the size of it, but let's put this way. There is a way to reduce the size. Do you guys know how to do that? I think appearance, zoom in. Yeah, zoom out, I think. Yeah. So now we can see the entire algorithm. Okay. So now let's see. You said let's go with the actual example. So we have 7 here, right? No, not 7. We have 3 here and 7 here and 1 here, right? 0, 1, 2. Correct?
Yes.
Yes.
So this is very small heap. We are this is a heap with 3 elements. So at the 0, 1, 2, at the root we have 3, and at the left we have 7, and right we have 1. So this is example. So hypothetically you are looking at the tree and you can say, hey, 7 is bigger. But how this algorithm find out? So this is top down. You just initially you have 9 here, you just replace 9 with 3, right? Now we need to do top down heapify. Okay, so how this does is this one. So we don't know how what is the length of this tree. It could be 3 elements, it could be 10 elements, right? So you need to go all the way from top to down of the tree, and you need to put the maximum element on the top. That is the main intention here. The main intention of doing this top down heapify is we are creating max heap. This is a max heap, right? So in this max heap we need to put the maximum element on the top. So now the algorithm works this way. First let's find the left child and right child, index of the left child, index of the right child. Okay, so you already know that. So left child LC equal to 1 and RC, right child equal to 2, correct? Now we have parent p equal to 0, right? So p parent equal to 0, okay, and we calculated left child, we calculated right child. Okay, so now we need to figure out the maximum out of all three, correct? So there are ways to find how to find a maximum out of three elements. You have three elements. Okay, these are three elements. We don't know what is the value of here. Okay, so how to find the max? What you do is we are assuming the first one is max. Okay, now we'll compare these two and find out which is the max. Okay, if this is max, this max is still pointed to this element. But if this becomes max, let's say the second one is the actual max, what we'll do is we will update max equal to this. Okay, that way after completing this whole step, the max is pointed to the right element, which is the maximum element, either the index of this element or index of this element based on the values, correct?
Suresh, one question here. Uh,
Yeah.
why do we need that the first condition in both the if condition, 124 and 127, left child and right child? Shouldn't that be taken care of? Like,
You mean you
we,
mean this one, this
yeah,
condition?
yeah.
Okay, okay. That's a very good question. I will explain that.
Mhm.
So first let's focus on this condition. This is very important. That's what we are trying to find here. Okay. So I will
Yeah.
explain this in a moment. Let me first explain the second conditions, and then I will come to this first condition. Okay. So what are we trying to do here is in this whole if condition, okay, we are trying to find what is the index of the max. Okay. So based on the value, if this is the big, this is the max. If the second one is the big, that will be the max, right? So after this whole if condition from line number 123 to 125, by the time you complete that, the max will point to the correct maximum index. Right now we are assuming this is max. At the line number 123, we are just saying max equal to parent. Okay, we are initializing max equal to parent. But after line number 125, what will happen? Max will change. If the left child is bigger, the max variable max variable point to 1, because in this situation it is bigger. Let's say instead of 7, if we have 0 here, let's say you have 2 here, then it won't change, right? Max is still pointed to 0. You guys following that concept?
Yes.
Yes.
Because we will change the max index only if the left child is bigger. That is the condition we are doing here. So once you find the index of the max, then you compare the max with the value of here, value of the other element. So that's how you find uh, the max between three elements, correct? So let's find. So just simple example, like if you in a normal way, let's say you have three people lined up, you need to find who is tallest. What you do first, you take the two people and you compare their heights, and you will see who is the taller, and then you compare with the tallest guy with the third person in the line, right? That's what we are doing here. So we will update the max only the left child is bigger. So by the time if you come here 127, we need to compare with the left child. We need to compare the left child. If the left child is bigger than the max what you found before, that means it could be the max could be here or here. So whatever the max, let's say out of 3 and 7, this is the max. That means max is 1. And after comparing these two, what will happen? Max becomes 1, correct? Because 7 is here, right? So max becomes 1. Now we need to compare these two. We no need to compare these two because you already figured out this is max. If you have 9 here, then 9 will go up. But if you have 1 here, what will happen? Max is still 7. That's why we are comparing. Is the right node is bigger than the maximum that you just found before this line? Is it clear, Karanya?
Yes, Suresh.
I know it will be tough, just kind of this is how it works. So now after this, what will happen? If the right child is bigger, that will be the max. We are updating max variable 3 times here. First, we are assuming the parent, and if the left child is bigger, we are resetting the max to left child. If the right child is bigger than that max, we are resetting the max equal to right child. So in this situation, since you have 1 here, it won't change. Max is still 1. Max is 1 because you have 3 here on the top and 7 here and 1 here. So max is equal to 1. Now what will happen at line number 130 is we are comparing. We at the beginning of these two comparisons, we are assuming we set parent equal to max. But we are comparing, is that parent is still max? If the max and parent are same, that means let's assume something like this. You have 100 here and you have 50 here and you have 60 here. So initially we said max equal to 0, and after comparisons does it change? Because it's 100 here, still max, that is max. So after all these comparisons, parent equal to 0, p equal to 0, and max is also equal to 0, correct? After all
Yes.
comparison, does it see?
Mm.
So that in the situation you no need to do any swapping, right? Only if they did not match. If they did not match, that means you reset the max to either it could be left node or it could be right node, we don't know. So that's where we are doing the swapping. We are doing swapping only if the initial assumption is false. That means parent not equal to max. If the parent is actually the max element, if the parent is actually the max index, you no need to do any heapifies anymore. If they are different, so we found a max which is not, look at this comment here, we found a max which is not current root. So we found a max with the 7 is the max, but that is not the current root element, right? So in that situation, what we need to do? We do a swap with the maximum number. So we are doing that swapping. So parent equals 0. In this situation, 3 here, 7 here, 1 here. So now what we do is we will swap those two elements, correct? So if we swap these, so 7 will come here, 3 will come here, because parent equal to 0, parent is 0 and max is 1. So 1 and 0 and 1, the elements at 0 and 1 will swap, right? So then what will become? So this will be like this, right? So now the graph will become like this. 7 will come here and 3 will come here and 1 is still there, correct?
Yes.
Now let's look at the other one. Again, after swapping, we are doing top-down heapify with the max. What is the maximum value here? Max is 1, right? So now we are doing top-down heapify starting with 3. Because this should go, we don't know, there could be a lot of nodes here. At this time, in this example, you have only 3, you are good. You're saying, okay, just 3 elements. But if you are doing top-down heapify with 10 elements, let's say our heap has 10 elements or 20 elements. You need to do this process until you found the leaf node. Okay, that's why we are doing top-down heapify with the maximum index. In this situation, maximum is 1. It could be, let's say, if you replaced on right side, maximum is 2. So that's why we are doing top-down heapify with the element you just replaced. Okay, now 3 is here. Now let's compare with the childs of the 3. Do we have any childs? What will happen is, if
Suresh,
you,
one question.
yeah,
Maximum will be 7, right? Which we have already put in the parent position, like root.
maximum is the index of the maximum element. What is the maximum here? 1 here.
Okay, okay. It is the index. Okay.
Yeah, sorry, I should call it index of max. It's not actually the maximum
Mm-hmm.
value. It is the
Okay,
index
okay.
of max. Yeah, that's a good point. Actually, I should rename this as the index of max. Okay. So
Okay,
now,
okay. Yeah.
index of max is 1 here. So now we need to see if we have any other elements in the downstream of this tree which are bigger than 3. Because if anything is bigger than 3, that we need to swap again, right? That's the main top-down heapify. Always like parent should have the maximum value, right? So that's where this condition come into picture. I will tell you. So now top-down heapify. Now let's look at this. Now top-down heapify is, so 7 is here and 3 is here and 1 is here. 0, 1, 2, and here is our 0, 1, 2, 7, 3, 1, right? So now we are doing top-down heapify with 3. Just forget about the rest of the tree, because we need to see if we have any elements here that are bigger than 3. If we have anything which is bigger than 3, we need to swap again, right? So that will do here. So what will happen? Right child will, so the parent here is, parent is 1, right? We started with max is 1 before. So now this
Yeah.
is a recursive function. So now parent is 1. What is the left child? Sorry, parent is 1. So that means left child, lf, lc equal to 2 into 1 plus 1, which is 3, right? And right child, rc equal to 2 into 1 plus 2, which is 4. This will be like that, right? 0, 1, 2, 3, and 4. If we have any children, that will be these locations. These are the children. Like, if I draw in a small like this, I can tell you. So 0, 1, 2, 3, 4. So the childs of this one is here, left child is here, the right child of this one is here, correct? Based on the formula, right?
Yeah, yeah.
So what will happen is, there is no elements here. There is no need to do that. So because in this situation we have only 3 elements. But how can we stop? This is the stopping condition here, because the current will tell you what are the number of elements in the array. So current is, if you remember last week we discussed about it. When you are creating, okay, max heap, this is initialization. When you are inserting the elements, we are inserting at the location of the current. So current is initialized with 0. So we will insert at the end of the heap, and we will do bottom up heapify, and then we will increment the current. So at this location, at this time, the current is actually, so 0, 1, 2. If you have these 3 elements, current will be 3, because the next element, it will point the index of the next element. Basically, when you are inserting, it will be inserted at the location of the current. If you insert in the future,
Yeah,
if you
yeah.
so this is the current will tell you where you need, what is the next empty element in the heap. Basically, you created heap with 1,000 elements. Let's say you have only 1,000 spaces, but you have only 3 elements. So this is the index. So the current is equal to 3 in this situation, because you already filled 0, 1, 2. If you want me to insert, I will insert at the location of the 3. Basically, this is the next element. So now what are we doing here is, you calculated right child, you calculated left child index. Is that less than current? That means you, if it is less than the, elements, if now in this situation right child is 3 and left child is 3 and right child is 4, both are greater than the current, right?
Mm-hmm.
So 3 is, so it's equal, basically left child equal to,
Yeah,
this is
left
also
side equal to.
left child equal to current, but this, but it says like less than. Only if the left, if the index is less than current, do these comparisons, because there is no point of comparing the values here and here, because that's not even initialized. We have only 3
Mm-hmm.
elements, right? We
Hmm.
have only 3 elements, and you basically you are trying to find index of 3, and these are there are no values here. So in this situation what will happen? So max is still, so we initialize max with 1, right? M equal to 1. So we are assuming this is max, and there is no elements here and here. So this condition never work, because this condition, the first condition is failed. If the first condition is failed, you don't even check the second condition. That's how most of the programming languages will work, right? So it's same thing here. The
Yeah.
first condition is failed. First condition is failed. You're out of, basically it's out of the elements. So you are trying to find a right node which is out of the current tree. Basically you are at the leaf node. So now what will happen? Is parent not equal to max? But parent equal to max here. So parent is 1, p equal to 1, and max equal to 1, because we are assuming this is max and that is max, because you did not even compare with any of the children. These are not actually the children, right? So there is no more children here. So what will happen here is, this condition will fail, and then it will return to the actual algorithm. That means you completed the whole top down heapify. You understood the whole concept here? This is kind of stopping condition. Basically,
Yeah.
you did not change the parent. As long as you did not change the parent, you no need to do any swapping. You no need to do any bottom up heapify. So in another condition here, let's say there are some chains. So I'm giving you another example where you have some child here. There is a child. There is a child here. The value here is 1 here, and the value here is 2. Let's assume that. So you are assuming 3 is max, and after comparing, again 3 is max, so it won't change, right? Because 1 is less than 3 and even 2 is less than 3. So parent equal to 1 and max equal to 1. In that situation also, you don't do any swapping, no top down heapifies. It will stop there. Even if you have 1,000 elements, it doesn't matter. Let's say one has another child, 2 also has a couple of childs, it doesn't matter, it will just stop here, because it satisfies the condition of the heap. It will do only one swap. You swap from the parent to 3. 3 will only come down from here to here, and it will stop here, because that is the maximum out of the children. So there are two instances where this can stop. One is there is no children, there is no more children. You already reached at the bottom of the heap. That is one condition. The other condition is the children are already smaller than the parent. You understood?
Yeah, Suresh.
Yeah, that is complex. How about you, Karanya? Is it still confusing, or did it help?
Yeah, Suresh.
Yeah. So that's the top-down heapify. That's the complexity. I think this is the one which requires a lot of thought and how to understand this whole logic. Otherwise, the other methods are easy, right? So do you have any other questions, Karanya? The other one. So this is the bottom of heapify. This is also similar, basically. So as I said, bottom up heapify will happen if you insert at the ending, right? If you insert at the end of the array, you just inserted at the end. Current is the end, right? But that could be the bigger element. We don't know until you do the bottom up heapify. That will go up. So basically, so this is a while loop. So where I equal to current, you start at the bottom. Let's say you added. So we have the heap like this, and like this. So now you added one element. Of course, this will add here. So you added one element here. Then this will go up based on the value. You started here, current is here, right? So while I greater than 0, basically these are all in a array format. All the elements here, you just added another element at the end of the, you just added at the end of the here. Oh, it's very big. So now you added at the end. So once you add the element at the end, you need to compare with the parents. That's what we are doing here. While I equal to current, right? And if I greater than 0, we are taking the parent. Hey, what is the parent? So this is the formula to get the parent, I minus 1 by 2. Then we'll get the parent and we'll compare with the parent. If the parent is smaller than the value of I, then we'll swap it, right? So we are swapping. If the parent is smaller, then we'll put here and we'll put the maximum value on the top and look at that. So we will do the swapping and then we are calling I equal to parent. So then we are calling, okay, let's take the parent value. Let's take the parent value. That will be the I, and then come again. We'll do the calculation here. What is the parent, right? We'll calculate the parent again and we'll compare with the parent. We will only swap. We'll swap only if the parent is smaller. If the parent is not small, you don't need to swap, right? This is the bottom up heap file. Clear?
Yes, Suresh.
Yeah, it's always like the best way is just to using pen and paper and giving these examples. As I said before, this is the only way. So putting these kind of indexes here, some values here, and iterating through each and every line, then only we can understand. Yeah, that's one way. And the other way is putting some breakpoints in wherever in your it could be in any environment. You put the breakpoints and see how this is working step by step. That's the only way to understand these complex algorithms. Yeah.
Suresh, while deciding on edge conditions, how will you construct them actually?
Which conditions? Where?
Edge conditions like if the uh, heap is completely empty, return, and
Oh,
the
the base conditions. You mean like
yeah,
base conditions? Okay.
yeah, yeah.
Yeah, that's what here is, right? So I equal to 0. That means like if the I equal to 0, you are keep on going to the parent, right? So if you go to the parent of parent, let's say I became all the way to here, I equal to 0. Okay, you already at the parent. Now the top root of the root. Now what root of the tree? So now what will happen? I minus 1 by 2. That means so 0 minus 1 by 2, which is like minus 1 by 2, right? So it is like greater than. So what will happen? I is basically is not even in the array, right? I is less than 0. So I becomes like either I is 0 or I is. So basically, let's say I equal to 0, then it won't even do this. Sorry, I think this condition will not execute, because if I is 0, which is equal to 0, so that is the base condition. So you compare only until I reaches 0. If I reaches 0, that means you already at the top of the tree and you don't need to do any comparisons, because there is no parent for tree, there is no parent for root, right? If I equal to 0 means you are at the root of the tree. There is no parent for root, correct? Following, right? This
Yes.
is the base condition. That is how to check the base condition. And here in the bottom of heapify, this is the base condition. I would say this is the one Aravind asked about it. Why we need this? We are going down. We will go down only if the right child or left child within the bounds. If you are crossing current, if you are crossing current, that means you already trying to check the nodes which are not there in the tree. If the left child is greater than current, that means you're already at the end of the tree. So let's say you are trying to find left child or right child of this node. There is no left child, there is no right child, because current is here. But you are trying to you are getting the indexes which are greater than the current. This is the current, and these are greater than the current. That's why you don't do any conditions. I know it is really tough to find the base conditions or the stopping conditions. Yeah. Okay. Yeah, these are the only two complex things, like bottom up heapify and top down heapify. And yeah, so the rest of the algorithms, actually you guys only concentrate on this main algorithm. So just you can simply say, hey, okay, we already have a heap in every language. Like we will insert k elements, we'll insert k times, and we will compare with the top. So get top is the one. Like get top will give you the top, but replace top will replace the top. So there are two methods you can say, hey, get top will not remove the top. Remove the top. See, it just
Recording is on.
yeah. So the get top will give you the top element, because we need to compare with the top element, right? That's why I created a method called get top. But if you found that top element is smaller, or see the top element is the bigger than the element you are navigating. So you started at k, and you are going to the end of the element, end of the array, and if you find a bigger element, if you find a smaller element, what we need to do, you need to replace the top, right? That's what you just explained. Hey, we have a method called insert. We'll insert the element into the max heap, and there is a method called get top that will give you the top element, and we will have a replace top that will replace the top element, and it will automatically does the heapify. If you look at the replace top, look at that. Replace top will replace the value at 0, and it will do the top down heapify. Because if you replace the top, you need to do this heapify to find the next maximum, because otherwise the algorithm will not give you the right value, right? So you are putting at the top at the 0th location, and you need to do this top down heapify to shuffle the elements to make sure they are in the heap format. Okay, so that's the main algorithm. This is the main algorithm. So, and finally, once you completed this, finally root of the max heap is the actual kth smallest element. You explain that. So there is a get top. So as long as you understood this main algorithm, we are almost good. So in any interviews, I don't think they will explain. They will ask you deep and ask you to implement the max heap. So I'm just explaining just curiosity, because it's very important to understand how these data structures are built and how they work. So that's why I explained this whole concept of top down, bottom up. Yeah, but from the interview perspective, this is good enough. This actual method here, find kth min using max heap, this is enough. As long as you understood all these steps, we are in a good shape. Any questions on this main algorithm, this particular method? Are we good?
Yeah, we are good.
Yeah, because this is what you need to practice more. So I will give you another similar, I can explain, but or I can give you the URL of the link of the algorithm. So this is the where is that one? Maybe I opened here. So similar question here. Oh, here. Okay. Kth smallest element in a 2D two-dimensional array. So this is the question I asked in one of my interviews. So it's a little complex than the normal single dimension array. See this one, kth smallest element in a row-wise and column-wise sorted 2D array. So it is little complex, but there are steps here. So let's go ahead, and if you have some time, maybe we can go now, or maybe next week, or you guys yourself, you can also, since you already know about this max heap, min heap concepts, you can try to understand yourself. So basically, the see this one, the difficulty is hard. This is the question I got in the company where I'm working right now. I did not solve it, but I explained the whole concept. So basically, let's see, given n by n matrix, this is the n by n matrix where every row and column is sorted in a non decreasing order, basically non decreasing, that basically increasing order. Okay, find kth smallest element in the given 2D array. So look at here, there is a 3, so 10, 20, 30, 40 and 15. So row wise and column wise sorted. What is that means is, if you go any row wise, this is sorted, and if you go even column wise, see the 10, 15, 24. So if you go this way or this way, it is sorted. Correct? So now if you find, let's find second maximum or second minimum. Is it the smallest? Yeah, what is the second minimum? Second smallest, let's say k equal to, so yeah, we can go as an example. So what is k equal to 3? We want third minimum. What is the third smallest element? Why it is
20.
20?
20.
Right? Because
10,
you
15,
start
and
with
20.
here. Yeah, so if you, so you can, if you look at here, you can easily say, because it started from row wise and column wise, this is the first smallest element in the array. There is, so 10 is the first smallest, because that's the smallest element in the array, because every element this way will be higher, and even if you go top down, that is also higher. So this is the smallest element, and this is the largest element in the entire matrix. It's very easy to find smallest and largest, because you know that this 0 0 is the smallest, and if you're going higher this way and also going higher number of this way, and at the end of the thing, this will be the higher. So but if you want the second or third smallest, it could be either on this way or on the other way, right? So what do you do here? 10, 20 here and 10, 15 here. This is the second smallest. 15 is the second smallest and 20 is the third smallest. And look at this. 24 is the fourth smallest, and here is 30 is the next one, and 32 here. So it could be anyway. It could be either in this row or it could be either this row, right? So that's how it is. So let's say seventh. Let's look at the seventh max. See, 30 is the seventh max. So first one is 10, second one is 15, third one is 20. This is the fourth one. This is 30, the fifth one. No, look at this. 24 is actually another one. So after 25, 20, 24, after 24, 25, right? And then 29 here. So that's why here 1, 2. So this is the 2. So first one is 10, second one is 15, third one is 20, 24 is the fourth, 25 fifth, 26th is 6th, 29 is 6th, and 30th is the next one, 7th. See how complex it is? So in any row and column, it is increasing order. If you look at here, 15 and 25, 35, 40, these are all increasing order. At the same time, 20, 25, 29, and 33. This is also increasing order, right? Any row and any column. Got it?
Yeah.
So if you look at the actually the algorithm is like, if you look at diagonally, you will have all the sorted elements. That I'm already giving you the hint here. Look at the diagonal. Diagonal means like if you cross the, let's say if you cross an arrow from here, see 10, and then 15, 20, 24, 25, 30, 32, 32, 29. Oh, and again, that is also not correct. No, this is not diagonal, because after 30, right, you got 32. So it's all different. This is not even diagonal fashion. So it's
So
all
do we need to traverse like the whole matrix, like to get
you
the?
you
Yes.
can, but that's not a right way. If you can say, if you want to traverse the whole matrix, right, you can do, but you cannot find, if you traverse normal, you cannot find kth smallest, right?
Mhm.
So
No,
only
that's what
one
I'm
way.
thinking. Yeah. how
Yeah,
to
one way is
put the
you can
element
sort
in.
the entire array. Sorry,
Yeah.
go ahead.
No, no, for that, basically, I'm thinking how to put the elements into the heap.
Yeah,
So,
exactly.
hmm,
Can we
So
convert it to 1D array and then shall we do that?
that's another, yeah, exactly. That is good
hmm,
approach. One approach is convert the entire elements, put it in a single dimension array, and then use the heap. Or you can put everything in a single dimension array and then sort it. If you sort it, that's a basic naive solution. If naive solution is, hey, put everything in a array and sort it. And then if we, I can give you fourth element, I can give you third smallest or fourth small. That's kind of, it's a navy solution, but it's not efficient, right? You are already, let's say you have only 25. You are taking another array of all 25 elements, right? That's
Uh,
definitely not an efficient solution. The taking the whole input.
else,
Yeah,
else we can take every column and row and then first finish it and then move on to the next column and row.
exactly. That is the main. That's the main input here. They already in a sorted order, row wise sorted, column wise sorted. That is the main input here. So we need to find, we need to construct a heap here. But definitely heap will help you. Like if it is first smallest or the last smallest, it's easy. But you can just take a small element and compare. But if you want fifth smallest or sixth smallest, it's always heap. So if they say kth smallest or kth largest, it's a heap solution. That's a, it's a blindly we can think. But how do you construct the heap? That's where the this will come into picture. So approach here. So idea is to find kth minimum element. Each row and each column is sorted, so it can be thought as a c sorted list and having merged into the single list. So the kth element of the list has to be found out. So approach is similar, only difference is kth element is found the loop ends. So let's see. The idea is to heap min heap. Interesting. They are using min heap, not max heap. So create min heap to store the elements and traverse the first row from sorted elements. Okay. And heap entry. Basically, they are putting everything in the heap. This is one approach. See, the max heap is the second approach using the building priority queue. Priority queue means like max heap, I think. See, there are different approaches. Go through this and you can find using array. Okay. So I need to go through this algorithm and find out. Okay. But this is very interesting,
yeah.
algorithm. Go through
Suresh,
this.
could
I will.
you share the link of this?
Sure. Yeah, I will share the link of this
Mhm.
one. So go through this. This is very important algorithm in the interviews. Yeah. But it will definitely use the heap. So go through this algorithm and see if you can understand. Otherwise, we can go through, next week we can go. So here is the
Suresh,
algorithm there. Yeah.
uh, since they have used minheap, I suppose minheap now is not such inefficient. So we can use minheap wherever we can appropriately uh, construct a efficient solution for a list, right?
Yes. So basically, if you want to find kth smallest or kth largest, heaps are the best solution. Yeah. Because basically the idea here is we don't want to sort the entire input. That's a really complex, complex procedure, right? And you don't want to take the entire you don't want to take the space of entire input. You don't want to take another array of n by n, right? That is another advantage. So the using the heap, there are two advantages. One is you no need to sort the entire input, and the second advantage is you no need to take um, entire the space which is equal to the input. You no need to take. You just need to take only the kth or little more further. So that is the space efficient, and also the complexity wise, the processing also faster. Those are the two advantages of taking the heap. Okay. So yeah, they are saying like algorithm is ideas to use min heap. traverse the first row from the start to end and build a min heap of the elements from first row. A heap entry also stores row number and column number. Okay, they are it's a little complex here. In every heap entry also stores the row number and column number. Now run a look k times to extract the min element from the heap in each iteration. Get minimum element from the min heap, find row number and column number of the minimum element, replace the root with the next element from the scan, column and min heapify root, print the last extracted element, which is the kth minimum element. Wow, it looks like so many steps here. So please
Yeah,
follow
it's
each step.
complicated, I think.
It's complicated. Definitely, it is complicated. See, that's why like people will ask. I don't know why they will ask these kind of complex algorithms, but the simple algorithm, as I explained, just a single dimension array, but this is a double dimension array. So, but if you look at the actual algorithm is like this, right? See, kth smallest here. So number of steps will be smaller, but we need to understand how this is working. So see, min heapify is there. Yeah, and they also explain the complexity. Okay, so you go through this, and we can discuss next week if you want. Or next week is actually I want to explain the last one, like first common ancestor. So this is also very important. So I can send you that link as well. Here is the first common ancestor. There are a lot of videos and all these things. Lowest common ancestor. So basically, let's say if I give you x and y here in this diagram, this is the common ancestor from the bottom. If you go from this node x node, and if you go from y node, where they meet, basically this is the node where the two paths will meet. That is the lowest common ancestor. So it's kind of, let's say these are the children. So y is there is one node here which is the parent, but these two, the green one here is the parent of these two nodes. That's where the x and y meet. Okay, of course from here everything is common. The other nodes are also common for x and y, but this is the lowest common ancestor. Why this is called lowest? Because from the root, if you look at this is where they are diverging, right? If you want to go x, this will go this way. If you want to go to y, from here it will go to the different path. This is the lowest common ancestor from the root for x and y. So that is the algorithm. So they will give you x and y, and you also have a reference to the root, and you need to find that green node. That is the algorithm. So these are all complex, but we need to spend time. It's not like small as something like if you can spend half an hour, 1 hour, it won't enough. So there are different algorithms. These graphs and trees are complex. You need to spend a lot of time understanding, and even if you understand the logic, understanding that even if you understand the algorithm, actual understanding of the code is again difficult. Even if you understand the code, practice is difficult, right? So those are the issues here. Once you go to the the complex parts, you need to spend more time. Okay, sounds good so far. It's already 9. I think it's already late there, around 10:30, right?
Yeah, Suresh.
Yeah. Awesome. So is that okay, Karanya? Any questions so far?
No, Suresh. Actually,
Okay.
I today uh, the internet was not there, so I went through some one of my old book algorithms. So
Okay.
the way you explained, it is so similar to the way you explained. They have explained priority queues. It is
Mm-hmm.
nice. Now, if I get back to it, I'll understand more. I'll
Sure,
share
sure.
the
Yeah,
yeah.
definitely. Yeah. I think priority queues is just another name for this heap. Basically, heap also called priority queues.
Yeah.
So sometimes what happens is priority, they will give you the priority. Like we are only creating min heap, max heap, right? Sometimes you need to create a heap based on some priority. Okay, so that is again a deeper concept. Basically, if you go to, let's say if you go to a emergency department, let's say somebody goes to emergency department, they will put in a priority of the emergency. Even though you have a patients of 50 people, if somebody came with a really big emergency, that's priority is important, right? It's not min or max. It is not like, hey, what is the age of you? If your age is 50, you will take it. If your age is 40, we will. It's not like that. It's not based on the age, or it's not based on some other prayer. So they will assign the priority. Severity. Hey, what is the problem? If you cut the finger, it's very important because it's bleeding, and that is higher priority. You will put other patients aside, and you will attack that patient. You will save that patient immediately, right? So that is called, you will assigning the priority. Basically, if somebody say, oh, just a small scratch, okay, you will put aside. You will give you like number 5 or number 6. That priority will be assigned, and then you put it in the queue, not in the queue. Basically, the heap will take care of that. Based on the number assigned, it will put in the particular order. Okay, so that's a next deeper concept. Basically, priority queue is like where you assign the some extra value to each variable. That's what the priority queue. Yeah, you go through the concept, and if you have any questions, let me know. We can explain. We can discuss again. Okay.
Yeah, Suresh, thank you.
Cool, awesome. Okay.
Yeah, Suresh, thank you for all the help.
Awesome.
It was clear to
Yeah.
me.
Nice. So I will send you the links, and please, go through them, and we can discuss this LCM, the least common ancestor problem, next week. So just read about this one also. Like, better to read beforehand, since these are complex algorithms. If I try to explain from scratch, it will take more time. But if you already have some idea, then it will be easy to understand. It's easy to go, right? If you have some ideas, yeah. I will send these
Okay,
links.
Suresh.
Okay.
Yeah.
Awesome. Okay. Good night. Talk to you later then. Yeah. Have a
Bye,
nice week.
Suresh. Bye, Arvind. Bye.
Bye. Good night.
Bye.
Bye.
Bye.